All right, I'd like to welcome you to EE 213, the follow-on course to EE 211, taught last semester. Last semester, we went through 10 chapters of the book Fundamentals of Electric Circuits, 6th edition, by Alexander and Sadiku. We're here at Kauai Community College, and I'm Bob Swanson. For this semester, my background is, so you know, completely in electrical engineering. All sorts, but ended with a specialty in signal processing. I've had both teaching and industrial experience, largely industrial experience, from small companies to large companies. So this semester we're already into the course, and the first chapter we pick up with chapter 11 in this course. There's already a lecture been published on that by Georgian Provinis, who taught E211. In chapter 12 now we continue the work of AC power. So we're dealing with power. Remember, in the first 10 chapters of the book, the first half of the course, we dealt with elements, Kirchhoff's law, Thevenin equivalence, Norton equivalent circuits. We dealt with AC circuits, but single loop circuits, as we'll see here. And so we were introduced to the ideas of impedance, admittance, resistance, vector algebra, and vector managing of the parts and of the circuits. This will be part one of probably a two-part series or piece on chapter 12. And let's get right into it. So we left off last time in chapter 11 with a single-phase, two-wire system. A simple AC source that had, in this case, a voltage source that had a magnitude, calling it V sub P, and it may or not have had a phase angle other than 0. Generally, in a single loop, the phase angle is less important, unless it is somehow synchronized to a signal someplace else. All right, but nonetheless, this is our single-phase, two-wire system. And we're pretty good at analyzing these because we can treat this just like a voltage source here on the left and some sort of resistance, which we generalize to be an impedance. So this is a complex number with a real and an imaginary part. All right, this can grow now as we head toward three phases, which is what we want. And we're interested in three-phase, of course, because that's how power is distributed, universally. Certainly in this country, in the United States, but it happens to be true in a lot of the world as well. So we move from a one-phase system that we're comfortable with. This was chapter 11 up here, the single-phase, two-wire system. Now we move to a two-phase system with 3 wires. And these could be any phases, but we know because a generator that creates the power that gets distributed, a generator is something rotating, a magnetic field rotating inside a set of fixed coils. And so those coils are set at some angle relative to each other. And a typical one in a two-wire system might be 90 degrees. Okay. I've clicked on to a diagram or a picture that's more typical of what will happen if you look outside a residential area anywhere here in Hawaii, but certainly anywhere on the mainland as well. You see something that's got a big transformer, which we're going to be talking about in chapter 13, mutual inductance. All you need to know at this point is that this is a transformer that takes some voltage on one side and transforms it to another voltage on the other side. The voltages can step up, they can step down, they can be broken up in a lot of different ways, as we'll study again, as I say, in chapter 13. But for now, look at this one example, 7,200 volts. I don't think any of us would like to touch 7200 volts, but something like 7200 volts is what's running. I'm looking out my window right now at my power lines, and there's a single heavy, probably aluminum wire set at the top of the poles. That's the high voltage or the high tension delivery system of power. It is one side of this 7200 volts. I've not measured mine. I don't think it's 7200. It might be, but this would be typical. It's somewhere up in the 10,000, thereabouts volts range. The other side of it would be connected to ground. This transformer is the big. I'm looking at one, and it's gray. They're typically gray, often battleship gray, hanging on the side of maybe every 5 or 10 poles. I can look around across a valley. I see a lot of power poles, and I see mine in front of me and at least one other down the road. So this then breaks the power down to be 240 volts. So this is about a 30-to-1 ratio in this picture, always an integer number. And more than that, then the 240 volts is broken in two by something we call a center tap. So it breaks it in two, and to the two very common 120 volt lines or voltages that we're familiar with distributed in our house, in the residential house. We also are aware that 240 volts is usually available in the house for things like clothes dryers, maybe the stove, the oven, that sort of thing, the range, and whatnot. And in fact, if you go to the power panel in your house, the breaker box, you will see everything to the right of this where I'm drawing with the arrow, the words line 1 and line 2 and neutral. All of this to the right is what occurs in the house. And you'll see that come into your service entrance in the house, go through a meter, and then pass directly all three lines into your breaker box. That's always one box, one place. There may be sub-panels, but there's always one box following the meter. Okay, again, we'll be talking more about these transformers. So in a two-phase residential system, our three-wire system, again, is to the right side. The left side is the way power would actually be distributed in the neighborhood. Okay, now another point I can make here, since we were talking about these phase angles, notice this is a three-wire two-phase system, and that's exactly what's going to be set up here. But notice now, and we'll see this for sure when we talk about transformers, these two, line 1 and line 2, are going to be 180 degrees out of phase. And you might intuit that because from line 1 to line 2 there would be no phase difference, except if I tap it in the middle and call that ground. Then I look this way. This would be positive with respect to that ground. And in line 1, this would be positive with respect to that ground. So the net of that would be 2 voltages. And if this is in the middle, like it always is, 2 voltages of equal magnitude, but 180 degrees out of phase. And that's what you have. If you take an oscilloscope and put it on your house lines, you can see this very thing. Very important for this whole system to work in your house that this neutral line be a true physical line, but that it also remain firmly attached. This is shown as a ground, firmly attached both at the wires up on the pole and at the wire on this side. This would be up at the pole, and at the wire on this side in your breaker box. If any of those gets loose, breaks free, or is even jiggling around in the wind or something, this neutral can end up floating, and the net effect will be that these voltages here, while they may sum to 240, they will flip around. They might be 110 and 130, this kind of thing. They'll add the 240, but they may not be equal, and so that can raise havoc inside the house. Things like that. Another example that the text uses of a two-phase three-wire system that could be made if you were doing it not through a transformer, but directly from a generator. The generator coils might be placed 90 degrees apart, in which case I would have these. So this would be a little odd. The phase offset would be 90 degrees. So that might be very interesting. Probably not too balanced, as we're going to be getting to here shortly. So the usual technique then in discussing this, as you move from a two-phase three-wire system, we want to get to three-phase, and we begin with it as a four-wire system. The straightforward connection, or the analogy from the two-wire system, is we just add another source and a load down here and share the neutral. Okay, and that's exactly what's happened here. Only now we're showing the voltage sources exactly evenly spaced 120 degrees out of phase with each other. So the basic three-phase system looking like this would come from coil sets exactly 120 degrees apart, and they would be delivering a power line and a common neutral. And we're going to discuss in the next several pieces of this lecture, the next several slides, what are these voltages and currents like, and how can we hook them up? What are our choices for hooking them up? Because we actually have two serious choices. This one is the most obvious and maybe the most intuitively satisfying because it looks just like a single. You can identify here the single loop, and now we just add another bigger loop and another loop around it with another source. Okay. The important thing is, and we'll see it again in the next slide, is that we balance the three-phase voltages. And we do this in the way that they are generated. It really doesn't matter whether the generators come from hydroelectric power or steam power or whatever. AC voltages, like the kind distributed in industry and residential areas, so commercial, is all done by rotating fields, rotating magnetic fields being intersected by fixed magnetic fields. So you have the rotor, basically in this simple example, an end-on view of such a three-phase generator. You got a rotor with a north and south pole. We've all played with these. And in this case, it would have three sets of coils on the stator. Notice the three sets are marked by A and A prime, so looping of the coil might go around like this. Right? The B set, same way, and the C set the same way. Now notice as one of the poles, choose either north or south. I'll choose north. And there's a little arrow here indicating rotation counterclockwise. Notice that the north pole intersects the A terminal, and then the C prime terminal, then the B terminal, then the A prime terminal, then the C, then the B prime. So it's not hitting A, B, C, A, B, C, A, B, C. It's hitting basically A positive, C negative, B positive, A negative, and so forth. And we'll see these in this picture, where it would be the simple rotation. If there was no coil except for A, you would get the solid line called that I've labeled A, or the authors have labeled AN. A time-varying signal at some frequency based on omega, the rotation rate of the rotor, and it will go through a complete sinusoidal shape or time waveform. The B one is the next intersected. So when you're trying to find phase angle in this arrangement, B is the next one encountered. Why? Because after A, the next positive or positively oriented piece on the stator that you hit is B. You're hitting the negative part of C. Then next you hit positive part of B. Look, physically 1/3 of the way around the stator. So 1/3 of the way later, if this is 360 degrees across one complete revolution and one complete cycle of the A form, 1/3 of the way down that, or 120 degrees, begins the B shape, and 2/3 of the way around begins the C shape. All right, so let's go a little further down. Let's talk about when the North Pole passes A and then also passes C prime before it gets to B. Let's try that. Let's get down here further a little bit. Here comes A, and it starts up again now. So it's just, where is it? It's just past the A terminal, the A side. All right, and we could ask ourselves, we're there. Where is C? Well, we're not aligned with C, but we're coming up on it, right? We're how far? We're not 120 because we're 60 degrees out of phase with C. So this would tell me if I anticipate A is here, after the peak of A, 60 degrees later, I ought to have a negative peak of C. So here I am, and you'll have to take my word for it, but this is 60 degrees. I'm a little bit down here. I'm 60 degrees away, and you could get out your protractors or mark things and calculate how much linear distance has passed there along the omega t axis, but it will be 60 degrees. You know, for instance, that from here, this peak to the B peak is 120 degrees. Halfway through it is 60 degrees, and lo and behold, that's where the negative of C is. So that's the alignment. And because this is a rotating fixed structure, the only thing that's going to change is frequency. The phase shift in orientation is definitely fixed. Okay? So, as I have my note here, convince yourself that the order of peaks is going to be ABC. The order of phase is going to be ABC. If I rotate it the other way, like this, then it will be ACB. The rotation I've shown here that I just described in the counterclockwise direction with the fixed rotor stator arrangement is called the positive ABC orientation. Rotate it the other way, and it's the negative or ACB orientation. Another simple way to achieve that would be to just interchange the B and C stator windings, but that would just simply be a labeling question, right? So, so they can present in two obvious ways. You'll have to think about the positive and negative one. I don't think it's a big deal. It's just a kind of a statement of how we want to orient the phase angles. All right, so we have three-phase systems now. They can present themselves. Three-phase we're thinking of as three generators, AN, BN, and CN. And you can hook them up in two obvious ways. And by obvious, we're really thinking of how do we hook them up so that we can distribute power, right? This isn't a little game that we're trying to play just for, a novelty. Think of all the ways you could hook up three generators. We're really trying to hook them up in ways that make sense for distributing power. And the Y connection, as I mentioned before, is probably the most intuitive. Here I've redrawn it to look like a Y, since that's the standard nomenclature and notation. But it's really the same thing we've been showing all along, the 4-wire three-phase system, where you just have a ground wire and you hook three terminals, three voltage sources up. A second way to do it is to hook the the three generators end to end, positive to negative, positive, negative, positive to negative. And that may seem a little weird because it's like, well, what happened to the neutral then? I kind of lost track of of where my neutral is and where are my loops. Okay, but notice the author and the industry cleverly relabels the voltages when they do this, and they call them A to B, A to C, and B to C. In other words, they don't measure from A to N, they measure from A to B, and then they measure from A to C and B to C. In so doing, they come up with a three-wire system called the delta connection. I've always held, even though I've done this stuff and I've watched it, never worked in the power industry, but I have to confess the delta connection has always felt a little odd to me. It's like, where did that wire go? Where did that connection go? But it turns out these two are closely related, and these AB voltages can be calculated from AN and BN and so forth. And in a balanced system, when loads and sources and all this are properly balanced, even in the Y connection, there's no current in the neutral line. So it can be sort of know that it's there, and in fact, we think of that as the ground. I mean, as I look out at my power pole and I see the transformer hanging out there, the first thing that's a little disconcerting is, well, there's only one line going in there. That's that 7,200 or 10,000 volt line. And the earth itself is considered to be the second line. So all of this sort of begs the question to me: why not only use the Y connection? If it's clearer, it's easier to think about, and all that sort of stuff. I think the obvious answer is the delta connection, just by its connotation, is only three wires, and it will always be three wires. So the delta connection is cheaper to distribute. The Y connection most of the time has four wires, although I just said the neutral line typically has little to no current in it. The reason you might stay with the Y connection, or at least consider it from a mathematical point of view, is when the systems get unbalanced. And that happens in large industrial loads or large commercial loads where you've got a lot of motors and this sort of thing, very much like the weight distribution in an airplane. You could have a load in the cargo of an airplane, and two airplanes, same model, same thing, may have the same load, but one may put all the load in the front or all the load in the back, and it will perform differently, if it can safely perform at all, from the same plane, same load, where they distribute the load across the whole belly of the airplane. Simple analogy, but balancing of loads when you're talking about large voltages, large currents, long distances, lots of distribution. You have something like this. This happens to be a picture of power distribution in a obviously barren spot in Alaska, this picture. But you see this, in long distance runs out in the Midlands and the Mid-States, on the mainland and across the Rockies and stuff. Sometimes these three poles will be one heavier duty steel structure, but you can imagine, here's the three wires distributing power. That's all that's on each one. And these are simple wood poles. And yet this is probably, given the space here, this is probably, I don't know, 100 kilovolts across here, maybe 200 kilovolts. People who study power and power distribution far beyond what we're going to in this course actually look at large, like blocks of power And in some cases, there's even been a lot of investigations done about transmitting blocks of power as DC and then unpacking it after a long distance and turning it back into AC. Because at the end of the day, it is still energy, right? And we saw that in chapter 11 when you have a sinusoid. As long as it's just a sinusoid, the average value can be 0. But as soon as it moves off of 0, or there's a phase shift between the load and the source, you can have a DC component, and then you've got power transmission. All right, so regardless of the Y or delta orientation, the relationship among the voltages in a balanced system, so I'll keep saying balanced because that means a lot, as you'll see when we do some simple calculations here with various arrangements. Nevertheless, the sources always remain separated by 120 degrees. So here's a summation. This picture is in your text of the positive orientation. Omega is progressing this way. The rotation of the rotor is this way. What you need to think of is as this three vector object, I would say, rotates counterclockwise, the next vector, the B vector, as it comes up here, crosses the 0 axis, so it becomes at 0 phase next from A to B. The rotation is this way. So that's a positive orientation. And these are the equations that get used for, now remember it, AN, BN, and CN. Okay? So all that matters, again, is the relationship occurs in a positive direction or a negative direction. And you can always think of it in terms of the rotor direction. Which way is it rotating? So quite simply, if we want the negative rotation, which would be ACB, all of the mechanics are the same. The rotation of this little, you can almost think of this as like the three blade propellers in wind systems, wind generating systems that keep rotating in one direction, and they have 3 big giant blades at 120 degrees. Well, C is the next one to orient. Clearly, all that happened was you reversed B and C. It's the same thing physically you would do on the rotor if you just relabeled the stator connections. All right, and so here they are relabeled. In fact, CN is now minus 120, and BN is plus 120. Even though it's plus, it doesn't mean it's next in line. It means it's already passed. Okay? So, a confusing thing about this figure, just as a final statement before I leave it, is that in order to keep the conceptual vector rotation counterclockwise, you just transpose the B and C vectors. Okay? So, with that, let's take a look briefly at the loads. I want to do that. Loads can be the same type. You've got the Y load and the delta load. I mean, this is just the only way to hook up 3 things, right? Unless you're going to make them all in series, but then you don't have 3 independent loads. The net here is you end up with 3 independent nodes. Now, notice, again, just like in the source, these 3 Z's, Z1, Z2, Z3, are here. And as you might guess, we're going to want those to be equal if the load is balanced. In the delta, we've got ZA, ZB, and ZC. We changed the subscripts from 1, 2, 3 to A, B, C. And that is because these are not, ZB does not equal Z1 or Z2 or Z3. ZB is something else. It's related to this, but it's not identical. So these 3 are going to be equal, and these 3 are going to be equal, but they're not going to be equal between configurations. They're going to be related, but not equal. Okay? So all load elements are equal, and the sum of them is going to be what we call ZY. And the same is true for the delta load connection. The sum of them is going to be Z delta. Okay, I had to take a break there and edit the slide. I had brain freeze and made Z1 plus Z2 and 3. So I renotated that, and you can see that this means they are equal, which is the intention. All right, and we might remember, you're going to see it again in a couple of different forms here, but you might remember from EE211, Chapter 9, we did do some things with Y and delta networks, or at least networks of elements, and they do transform in this way that Z delta, if I look at any of the elements over here, ZA, ZB, ZC, is equal to 3 times ZY. And so conversely, that ZY, the elements Z1, 2, and 3 are each 1/3 of the respective elements or any of the elements in the delta configuration. Okay, you can go back and look at that. It's late in Chapter 9 when you did that last semester, so here is the reference. All right, let's take a moment here and do practice problem 12.1. It's not difficult, but it does get us into the habit or into the perspective here of drawing pictures and solving some problems. So we've got Bn is given, so that makes it a little more interesting. They didn't give us the first one. At 30 degrees and a magnitude of 220, find the other two values. So as you will see from me and problem solving kind of all semester or throughout, I love to draw pictures. They're the things that kind of cement ideas in my mind. So this is the omega t thing going on here. And what does this say? I don't need to draw the old ones. All I need to draw is what I know, which is VBN is here, right? I'll just put it on. I don't know what that little glitch was as I get used to using the pen. So there's VBN, and this is 30 degrees. The magnitude, of course, is 220. Now, if we know that there are two other vectors, and the system is fixed at 120 degree separations, 30 needs another 90 down this way. So there must be another vector down here. We don't know what it is. We'll hang on to that judgment for a moment. Okay. And here's another one over here. This is 30 degrees. So we've got our 120, and of course 120, and the last 120. Okay, so our only question is, which ones are these two, right? And we're saying we've got a positive sequence. So now down here, remember VBN trails VAN. So the rotation is still this way. So this must be AN over here and CN down here. So aside from VBN, what have we got? We've got, where's my pointer? We've got VAN has got to be the 220 we know. And the angle has to be, what, 30 plus 120? Got to be 150 degrees. And VCN has to be, it looks like, minus 90 degrees. 220 at minus 90 degrees. And yes, that's what they have up there, as you can see. Kind of easy to keep track of. So you can relate this diagram here that I drew, you can relate that to the one of previous slides or ones earlier in your text. And you can see. So that's easily problem 12.1, just a practice to make sure. So I emphasize drawing the diagrams. I mean, unless you're doing 2 or 3 problems that virtually use the same diagram and you can relabel some things, I'm just always cautious about having good diagrams. It keys your thinking. It's something to check yourself with and hang on to. So now we got to hook up balanced loads, various loads with various sources. And we have 2 configurations, the Y source and the Y load, the delta source and the delta load. So there's 4 combinations of 2 things, right? 4 source load pairs, and here they are, Y to Y, Y to delta, delta to delta, and delta to Y. Some of these may seem more natural. Some of them, the math maybe is enough straightforward that it really doesn't matter. This is what you're going to be doing anyway. Y to Y, they always start with that, and I think for the reason I mentioned, it's kind of the most intuitive and maybe the most straightforward to go with. So let's look at that. From the text, I actually took his figures out of order because I think it makes more sense. The basic YY configuration is just pretty obvious looking. You've got sources over here, and you're on the left, and you're going to match them with a load on the right. Okay. Now, what typically happens, so if you want to account for everything, which I suppose at the beginning we need to do, you can see buried in this, which I think was probably figure 9, just a whole lot of rectangular boxes, which means they kind of, what I call fully outfitted the YY combination. In other words, there's a where am I at? Oops. So there's source impedances here. And that would be like a Thevenin impedance in this case, because I have a voltage source and a series impedance. So that's a Thevenin impedance, right? A T source. Then over here I've got, what have I got? Looks like it's sort of in a triangle, but it's not. This is actually the line impedance. I'm not sure what the label is here. The ZS kind of makes sense. I don't know if that's a script L, I guess so, like a line. And then over here is the capital L, so this is the load. Okay, and that is one complete sequence. I've chosen to annotate the B sequence coming down here from the source. Here's the loop going around here through the load and back through the neutral. Oh, and just to be complete, they put an impedance in the neutral line. Now, as he mentions, typically for power to be delivered, and you might remember this from, you want to be able to get the most current out of it, but typically source and line impedances, like here and here, are kept very, very low. Very low means low in comparison to the load. So that quickly takes you back over to, if I can find myself, over to this, the basic YY. Okay, but you can bet, and it's true, we're going to be doing a bunch of problems right off that are the fully outfitted ones, just to show ourselves that low impedances in the source and the line quickly get swamped out by the load. And you can kind of look ahead and anticipate what's going to happen. You've got small impedances here running against a large impedance on the load. Even if they're complex, which they are, the load is going to kind of swallow them up. That's really what the author was trying to indicate. All right, so now let's do some of the relationship first between line and phase voltages, if we might. And what does that mean? That means I'm interested, if I can find myself here, I'm interested in finding VAB, right? This is notice I deliberately picked a Y configuration where the sources are all hooked up as point to neutral. And now we're going to want to find AB. We're going to want to find this voltage across here, right? Something that looks a little more like the delta. So it leads ahead. But we're not doing a Y delta. We're doing a YY, but it doesn't matter. We're finding the line-to-line voltages because that's always helpful to have, and that's always what's going to be out on the power lines. That's always what's going to be going on out there. So if I look at the VA to B, what is it? I've got VA to neutral plus, so just, draw your finger around here. I'm starting here, and I'm going up here to this point. Then I'm going to go down here to this point and work my way back to the neutral. So I've got VAN plus VN to B, right? In other words, I just unpacked this in terms of two summation voltages that I can do. All right, but I could write that as VAN, because I know that. It's some VP at an angle of phi. But then I could just subtract V B to N since I have that. Right? And what does this amount to in our simple example? I'm going to say that there's a magnitude on these things of VP. So VAN will be VP at an angle of 0 degrees. And then I'm going to subtract. I have this one in terms of the same terms, so that's going to be VP at an angle of, what was this? Minus 120? Okay. But a minus 120, maybe we better start drawing some of this and augment this figure a little bit. So I'm going to do that here. Right? Here we've got VAN. Right? And here we've got VBN. Okay, so this is 30 degrees over here. All right. Now if I want to take minus, by the way, just for reference, I guess we could stick our VCN in here. But if I want minus VBN, in other words, I want VNB that I'm going to add, or I'm going to subtract minus VBN, what is that? It's actually the vector, so this is VNB, right? It's actually the vector run up here. And if that was 30 degrees, this is 90, this is what, 60? Do I have that right? Yeah, because I'm flipping 180, right? Going over is 180. My mind suddenly thought of 120. It was like, oops, no. By negating it, I'm flipping 180 degrees. So 30 plus 60 is 90, plus 90 is 180. So now I have VNB. So now what I really want to do, according to this, was add these two vectors. Add VA, there it is, and VNB. That's what I was doing up here right away. I'm adding those two. Well, let's draw that picture in terms of vectors. Here that is, right, a parallelogram. So here is what this sum is going to look like, right? And we know because it's a regular parallelogram, we know a lot because it's equal sides too, that this is 30 degrees, right? So right away we know that our V A to B is going to be something, we're going to want to fill that blank in, at an angle of 30 degrees, right? We know that before we even get too bent out of shape. So all we need to do now is find out what's that angle. And as soon as we have that one, of course, then we do our 120 degree thing, and we can go back here to the next vector. If that's 30, if that's up 30, right, the next one will be 30 up there. And we'll just keep going around, right? We'd have 60 and 60, so the next one would probably be over in here, right? But this is the one we're concerned about right here. How do we get VAB? And we need this magnitude, and we're home free. Okay? So we were doing something good along this line up here. VP at 0 degrees. So what is that? That's VP. Whoops, VP. And at 0 degrees, there's no imaginary part. Then it'll be minus VP, P, not O. Well, we can say it's plus. We now have the actual vectors there. So if I'm subtracting VNB, I've really got what? Plus VP times whatever the real projection of this is and whatever the imaginary projection of this is, right? We want that, and we want that. Soon I'll learn how to change pen colors, and then I can really dazzle you with that. Let me show you something here, though, that's going to be handy. You know I'm big on estimating things and kind of figuring things out without... Whoops, where's my pen? Way over there. Okay. Here's a simple... There are certain things that are, worth learning. This is a right triangle. All right? And if the dimensions here are 1 and 2, the dimension here is what? 2 times 2 is 4, minus 1 times 1, square root of 3. Okay? So this is one of Bob's favorite standard triangles, right triangles, 1, 2, and the square root of 3. I really like it because this angle is 60 degrees. This angle is 30 degrees. And so without even having to haul out my calculator, look up trig functions or any of that stuff, I have a good handle on the problem. I know the angles create these side lengths, so I'm in pretty good shape already. So what do I know when I break up VNB? I want to add VNB. I know that, what have I got here? This side is going to behave like the 2 in my triangle. So that means this real contribution is going to behave like which? The 1 or the square root of 3? It's going to behave like the 1. Right? So the real part addition is going to be 1 plus j times the imaginary part addition. Right? That's the square root of 3. Okay? But now my triangle didn't have 2 as a hypotenuse. It had 1 as a hypotenuse. So I can fix all that by just dividing this by 2. Okay? And so where does that lead me? It leads me to hopefully something that involves this triangle again. That would be nice. So I've got VP times what? 1 plus 1/2. So 3/2. Right? And plus j times the square root of 3 over 2. Right? So I can look at this now and I can say, how is this? Is there something convenient? Well, maybe if I pull out the 2, make this VP over 2. It will look a little better. And perhaps if I pull out a square root of 3, it might look a little better. And if I do that, if I pull a square root of 3 out of here, this is going to be 1. And this is going to be square root of 3, right? So if I have this as square root of 3 plus j. Okay? And if I look at this little guy right here, what is this? I've got my 1 something in the square root of 3. Here we are back to our little triangle again. The imaginary side is 1 square root of 3. We know this is 2, right? So the magnitude of this thing is 2, and 2 times 2 gets rid of that, right? So let me do this all legitimately here. This all becomes 2, and 2 dividing 2 is 2. So this all equals square root of 3 times VP. Okay? So that is the length of that new vector. So VAB, as a function of the phase voltages, so the line voltage, by line voltage we mean line to line, as a function of the phase voltage, has an angular shift of 30 degrees, you see it here, and a magnitude increase of square root of 3. Okay? Good things to know. A lot of this, you don't even have to get sight. You can stay with pictures and, getting comfortable. There are a handful of these. The 3, 4, 5 is another one. 5, 12, 13 is another one. It's triangles where the sides turn out to be like integer numbers, not crazy fractions. Square root of 3 we can handle because we like it. Same thing with the 45, right? A right angle 45. It's square root of 2 and square root of 2, 2, 2, and the square root of 2. It's that sort of thing. So you like to keep that stuff in mind, or 1, 1 and the square root of 2, I should be saying. Yeah. So some things like that you'll just keep in mind. They're not hard to remember, and they're really handy because they keep your mind focused on the problem solving. Okay? So here is this all summed up in pictures, a cleaner picture of what I just did. These pictures are in your text. And the complete diagram for 3 phases. So you can figure all these out, how they go. We drew this one. And once you have that, it's just a matter of saying, well, this is 120 degrees. So if that was 30, we know that's over there at 150, right? And this guy's down here at 90. Okay? But we knew that. Nice thing about this, it enables us to think back of single loop circuits, right? So here was one, back our original one stated again. This is in terms of a phase voltage, but we can do all the substitutions, because this is a Y value here. We can do all the substitutions and make this source a VAB kind of source, and switch this to, whoops, where are we? Switch this to a Z delta, right? And we still keep with our single loop things, but we've now shown a very easy relationship, direct relationship between line voltages and phase voltages. And it isn't going to matter whether it's Y or delta. I want to just go to example 12.2. This is in your text. I'm not going to bleed us through this, but I did want to point out here a couple of things. Where am I at? Whoops. Here, this is a fully rigged out one with the neutral line removed. And here is the source impedance. Here's some line impedance. And here is, oh, no, I'm sorry. they put a source and a line together as small values, and then here's a load impedance. So this is load, and this is source plus line. However, that's to be considered. And you can see down here, where am I? You can see that all of this can be considered as, right? All of this can be considered as some net Y impedance, which is the sum of those two. Because if you keep backing it all the way up, whoops, and make your loop here, you start here, and you go through the source, and you've got these two are in series, and you get back to this point, and this point, whoops, is a neutral point that connects back to here, right? So if we're going to do it as how much current is in line A, we can just treat it as that way. And so that's all that's going on here. This is reduced here into some very complex phase shifted Z. We haven't done that before. We've been comfortable with 30 and 60 degree things. And so the current is simply the quotient of those two, so a small value and this really odd angle. Okay? But once you have that, the 120 degree phase shifts easily gives you all the rest. Okay? So I don't think I need to say much more about that. We'll take a short break here, and I'm going to come back then and do practice problem 12. Okay, I'm back, and you can see, if you've been staring at the screen, that practice problem 12.2, the reason I wanted to go through it was because this really is an example of the fully loaded Y source, Y load with source and line impedances included. Okay, so now I am not going to draw the huge diagram. You can do that yourself because I've already shown and described how we can break this out into single circuits. So I'm just going to draw you one piece of the Y. We'll start down here at the neutral and put our source in here, our nice AC source, plus and minus. And they say this source VA to N is 120 at 30. Well, okay. There's our other side. We'll put the plus there. And there's also a brick of source impedance, which they say is what? They want a three-phase generator. Has an impedance of 0.4 plus J 0.3. So this is the generator, 0.4 plus J 0.3. Now you can see right there, this is suggesting to my little mind 3, 4, 5. So whatever angle's involved here, I know that the magnitude of that vector is 0.5. Don't know that we're going to get to exploit that fact too much here, but we'll keep it in mind. All right, then it gets out here to the line. So that's the end of the generator between there and there. And then there's the line, and it comes out here to the load, and that will connect back to the neutral. Okay, now you can say, well, where's the neutral impedance? In a single loop like this, it's just bunched in here. So the line joining the generator and the load, it says over here, has an impedance of, 0.6 plus J 0.7. Okay, now this is not a friendly looking triangle to me, so I don't know how much hope I've got. The one thing I noticed that I like is 0.6 plus 0.4 is 1, and 0.3 plus 0.7 is 1. So that's looking a little more like a 45 degree right triangle. And our load is 24 plus J 19 ohms. Okay? So right away I see this is a lot bigger than this combination. So unless I get real nicky-picky in the work, I'm probably going to be looking at this. We're going to see that this load swamps out that. All right. So here, let's go then. IA is equal to what? VAN over ZY, where ZY is all of that stuff put together. So ZY, let's take a moment for that first. Before I get that, let's get ZY is equal to what? 0.3 plus J.4 plus I have these backwards. This is 0.4 and this is 3.3 plus 0.6 plus J.7 plus our actual load, the big guy, 24 plus J19. Okay? So this little part is what I said before. This is 0.4 plus 6 is 1 plus 24. So it's 25 plus J. 1 plus 19 is 20. Okay? So now I've got, this recognizes to me as a 4, 5, but unfortunately neither one of those is the hypotenuse, so it's not going to help me out. Okay? Did I do something wrong here? 0.4 plus 0.3, 0.6 plus 0.7, that's 1 plus 1, 25 plus 21. Okay, and I'm going to have to look at this and figure it out, but I know that it's about 32, and this isn't one of my estimates. I did something like this a little bit ago, and I think this is about 39 degrees, right? We can look this up as a double check, but it's something like that. I could kind of guess 25 squared is what, 625? Plus 400 is 1025, so that's about 2 to the 10th, so 2 to the 5th squared. So this is going to be about right. And the angle I can only guess at. Whoops. Okay, so ZY is, I'm guessing, about 32. I'll call it 39 degrees. Probably going to end up about 40. So what does this mean? It means that, I'll just say, therefore, IA is whatever VAN is, 120, at an angle of 30 degrees, and divided by 32 at an angle of, what is it? I'm calling that 39 degrees. Okay, so so this is what, a little less than 4. I'm not sure what that answer will be. Is something a little less than 4. So how much less? I don't know. 3.8, something like that. I don't have a calculator in front of me. And this looks like it'll be minus 9 degrees, thereabouts. Okay, so then IB is going to be equal to, in kind of obvious fashion, the same thing, 3.8, except it's now shifted 120 degrees back down. Remember, A leads B, so I'm lagging 120 degrees, so this will be minus, 129 degrees. And IC will be 3.8 at an angle of, if you have 120 degrees and you add 9 to it, you're at what, something like plus 129 degrees. I think I've got, whoops, plus 129. No, I'm minus 9, so 129. This will be, whoops, 111 plus 111. Okay, about that. All right, I'll leave it at that. Now we need to get the voltages. So we've got our currents. And really, you can see already, we've got the currents. This one just comes down to cranking out some full value of Z and getting that in a form. Now, what do we want for voltages? That gave us line currents. We did them in backwards order. So now we want line voltages. Okay. And we know the line voltages. We just got done calculating all those relationships. Right? Remember, I'll just reiterate them here. VAB is VA to N minus plus V N to B, and we go through all that bit. But we got from all of that the line voltage, right, the voltage across the line, right, is, and we're talking now line to line. We're not, you have to get your mind off of this simple circuit. It's not line to neutral, it's line to line. Line to line. All right, and that we know, because we just got done doing it, is the square root of 3 times VP. And that's, what, 120 times the square root of 3. So I do have a calculator now. That's 207.8. All right, and now all we have to do is get our angles. So V, what do we got? VAB at first is 207.8 at an angle of, what's our first one? If it was initially 30 degrees, where is that? 30 degrees up here. Remember our little picture? It migrated forward another 30 degrees, so this is going to be 60 degrees. And you can go directly back to the picture. You don't even need to, that we already did, right? That showed when I calculate line voltages, line-to-line voltages from phase voltages, there's always an advancement of 30 degrees from the first phase voltage angle. So if the first was 30, I add 30 to it and I get this. Okay? Then V, well, so we got VB to C is 207.8 at an angle of, and I take VB to C and add that angle. I could take it as, what is this? A minus 60. Right? Probably this is going to be minus 60. A to B is minus 60. And again, just go back to the drawings and you'll see these. And then VC to A is 207.8 at an angle of, what have I got? If I've got 60 and I've got minus 60, then I must be, what? Plus 60, minus 60, I must be straight on the back axis, so that's minus, minus 180 degrees, or plus 180 degrees, whichever way you want to call it. All right, so I'll peek down here and say, all right, here we are. You saw that unfold. I did a little estimating, so I came up with something not quite 375, and I probably have maybe a little difference in this if I really look at this close. That's the determining factor there, but it's just a matter of how much you want to keep with it. So that is how I would flesh out that problem, and then we've done now a Y to Y load, balanced load, and we'll next move on in part 2 of this. We'll finish the chapter doing the other 4 load types, Y to delta, delta to delta, and delta to Y, and then complete the chapter with a lot of examples in that way. Okay? And then look at power. We do need to look at power, but power is, comes down to just getting all of these values straight. So that will be it for part 1 of chapter 12.